Hi everyone, welcome to this special experiment we're going to do today called canned parabolas. In your math classes you have probably been studying the topic called functions, and one of those functions that you studied was called a quadratic function. And the graph of such functions, as you know, is a parabola. Now, we'd like to put some of that math knowledge to work. And the little experiment we're going to be doing today is we are going to roll a ball down this ramp, and what we wish to do is position the can so that it rolls off the ramp and the can catches it. Now, just to get a little idea of how this is going to work, we're going to try it without mathematics first. So I'm going to roll the ball down to make it fair, and Melanie is going to watch the projection. And then, based upon eyesight, she's going to try to place that can in the proper place. And if she can do it, I guess mathematics is not needed, but we shall see. I will go.
You chose me with bad eyesight, didn't you?
I will go to the top of the ramp, and Melanie is watching, and she can kind of see where it landed. And now we'll give her a chance to position the can where she thinks it ought to be in order to catch the ball on the next roll. You like it in that position, Melanie?
Yeah, I think that works well. My eyes aren't that bad.
Okay. We'll make sure we started at the same spot.
All right.
And unfortunately, it was a little bit shy of where it had to be. Okay, now the question is, how can we use your knowledge of mathematics to figure out ahead of time precisely where that can has to be placed so that when we roll it the next time, it'll land right in the can? Okay? Now, the first question we have to ask is, when the ball leaves the ramp at this point, what path is it following? That's what we have to discuss first. And Melanie, what do you think the path is?
Well, since you said that we were talking about quadratic functions, which I believe we are, now I didn't see it very well, but I think that it ought to be a parabola.
A parabola?
I do.
And do you remember what an equation of a parabola looks like in general?
Yep. Y equals ax squared plus bx plus c?
Okay, that's what we learned in the math class. Now, if we can find the proper equation to follow the path of this ball, then maybe we can project right where that can has to be so that we can land it right in the center of it.
Okay.
Okay, now, we could draw this parabola on a graph in various ways, and that's what mathematicians, applied mathematicians, technically do. They try to go to their drawing board and make a little model of what's going on.
Okay.
So if you would start making that model.
All right. So I want to set up some axes.
I think so.
I'll locate, this is the x-axis.
Okay.
And this is the y-axis, and this will be my origin.
Okay,
right
now the question is, what would be the best position maybe to put the vertex of our parabola to make the calculations maybe as easy as possible?
Well, I personally think that when we have a linear value here, that it makes things a little more difficult.
I agree.
And so I'd prefer to have one that doesn't have a linear value. So if I can put the origin in the middle, or not the origin, but the vertex of the parabola in the middle, right on the y-axis someplace, I can eliminate that part.
Okay.
So maybe if I put the vertex right there at 0, 0. Does that work?
Okay, so what would be the path of the parabola if you were to draw it then at this point? We're going to put the vertex at the origin.
So we're coming down the ramp from over here?
Yes.
We come down the ramp from over here, and it launches at about this point.
That's what we'll try to do.
And then probably comes down like so.
And eventually it hits the lower table.
Okay, let's put the table in there.
So you're going to draw the level at which it hits the table.
All right.
Okay. So what we're trying to do then, I guess, is find an equation to represent this path that Melanie drew in red.
Okay.
Okay. Now, I guess the question is, what does the equation of your parabola become if we put the vertex at the origin? You said it's going to make it quite a bit simpler.
Well, it's going to make it easier. So then I think I can do just y equals ax squared, with this being some kind of...
Okay, so you may recall when we studied this in class that if the vertex is at the origin, you have a much simpler version of the equation of the parabola. And it just becomes y equals ax squared. So what do we need to find to identify the precise equation for the path of my ball here? What do we need to know?
Well, since I already know where the vertex is,
okay,
that part's known, then I think I just need one other x and y value, or one other point on the parabola, on the red line, in order to find the a value.
So if we could find the a value, then we'd have the precise equation for this particular model that we're doing.
I think so.
Okay, now we've got to figure out a way to get another point on that parabola. Well, we use this point right up here as the vertex, and that's at the origin. And then this ball came through the air and landed down here somewhere. So if we could mark the point on the table where the ball landed,
okay,
then by doing some measurements, we could get another point on that parabola.
All right.
But how are we going to make the ball leave a mark? Well, maybe something which they used to use in the old days before computers.
Way before me. Oh, maybe.
A piece of carbon paper, and when the ball hits, it should leave a mark.
Okay.
Okay, now, because the ramp tends to flex a little bit, and you know, it's pretty hard for a human being to be precise every time. We may roll this a couple times and just to make sure that we are in a good place.
I think you need to call clear before you do that.
Oh, sorry. Okay, trying to simulate it again. Hopefully it'll land on the same dot. And we'll lift the carbon paper and see how we did. We won't remove it just yet, but they're marks and they're very close. Maybe we'll just kind of compromise and go halfway in between.
I agree.
Often happens in real life that, you know, measurements aren't quite like they are in a math book, but it should still work.
It's good to me. Can we take this away?
Okay, I think we can remove the carbon paper. And while Melanie is doing that, we have to think about how are we going to find coordinates for that point that we just marked with the carbon paper and the ball landing on it? Well, let me see. The vertex is here.
Yep.
And so it looks like if we stay at this level, we're staying along the x-axis.
Okay.
Okay, so if I could find the distance from the launching point to this, then I'll have the x-coordinate, and then I guess the y-coordinate would be the distance from here down to the table.
This green line here is the table, and that's the vertex, so we want to measure along here on the table for the x-coordinate.
Okay.
And we want to measure from here to the launching point for the y-coordinate, right?
Okay, you may have been wondering why we have these pendulums hanging there. Well, you see, we knew we had to measure eventually down from the launch point to here, and the pendulum marks the point directly below. As I said at the beginning, precise measurements is one of the keys to a successful experiment. You fail to measure properly, and you might have a car that runs like a GM product or something. Okay, I have my tape here. And I came around to this side, and we're putting it on the bottom, following the pendulum.
Do we need the ball to see where the bottom of the ball is?
That's a good idea, because the ball has some diameter to it as well. So if you can...
I'll hold the ball.
Okay. And if I look at it carefully, now, where would we want to measure? To the top of the ball, the center of the ball? Well, what has to clear the can?
Well, the bottom of the ball has to clear the can.
So that's probably the part we better keep track of.
Yep.
And that's 29.5. Okay. So I'll take the ball, and if you could record that. Okay, well, Melanie is recording that. We'll take our straight edge here, and we will mark a little line. And then we will measure along that line from the base of the plumb bob.
I'd say 44.5 would work out well.
44.5. Well, I'm not quite here.
Not quite. 44 and 5/8.
44 and 5/8.
That's between the two.
Okay, 44 and 5/8 is what we'll record.
Okay, so that's our x value.
Mm-hmm. Okay, now we have to be very careful because we have to find the point that Melanie is marking now. And we need to attach coordinates to it. But you must remember where the x and y axis are. So what would be the coordinates of that point?
Okay, well, the x value comes across this way.
Okay.
So that's 44 and 5/8.
Okay.
Okay. And the y value, let's see, if my origin is here and I've gone down, so then I have to make that negative, right?
Oh, good.
Okay, so negative.
Good point, yeah,
29
making that one negative.
and a half.
Now, how are those values going to help us find the value of a, which is what we were really after?
Well, if I put the y value in here
Okay.
and the x value in here, then I only have one variable left, so I ought to be able to solve for that.
Now, you notice how in a real-life problem, the measurements are not like a textbook where
Oh, that's
it's
too bad.
40 or it's 25 or something nice like that. They tend to be measurements that are a little bit nasty, but then maybe that's why they invented calculators. So this might be a good place to use a calculator. So if you would show us what kind of an equation we'd have to solve for A, we'll proceed to do that. And I'll tell you the values that you need after you plug them in.
Okay, so for the y value, I'm going to place that in this equation here. I'm going to do negative 29. Do you want a decimal at this point?
That's an easy one. That's
okay,
fine. I can type it in either way.
29.5 equals the a value we don't know. The x value is 44 and 5/8. So we have a half plus another eighth.
Of course, 5/8 is 0.625 if you want to use that.
625. And we want to square that.
Okay.
So to solve for a, this number is attached to the a by multiplication. So to undo that, we're going to divide. So I want to take the negative 29.5 and divide by this amount, and I'll have that solved for a.
Okay, I'll get that entered in the calculator. Negative 29.5 divided by the quantity 44.625.
Squared.
Don't forget to square it. Okay, and I get an answer of negative 0.0148. Negative 0.0148. So what's my equation that models this parabola then? I think we've got it.
Okay, so we have y equals negative 0.0148 x squared.
Okay, that's the model for this projected curve that the path of the ball takes.
And I'm very glad that it came out to be negative, since our parabola is open downward.
Oh, yes, parabola. That's what we said in math class.
Perhaps we are doing something
right.
right.
If the parabola opens down, the coefficient of x squared has to be negative.
Good. Something's right.
Now, we need to position the can somewhere along this path.
Okay.
Now, if you look at the can here, you'll notice we have a plumb bob hanging from the bottom. And the first thing we have to do is measure how far is the top of the can above the table. And we're measuring this now, and it looks like
13 3/4 maybe?
Okay, we'll try it from both sides just to make sure.
Yeah, that side's a little higher, so I'd say let's just go with 13 3/4.
Okay, 13 3/4 from the table to the top of the can.
Okay.
Of course, we're measuring to the top of the can because we want the ball to clear this upper lip here if we can.
All right.
Okay. What coordinate should that be on the curve? So kind of project on the curve whereabouts the can would have to be located, the top. Okay.
Well, so it's probably in here.
Okay, we'll mark a point.
Someplace. So if this
Well,
is
that's the distance we measured, isn't it? Yeah, that's right.
If this is the can,
a little tricky
up to
here.
that point,
And what measurement was that?
13 3/4.
Okay, so we can mark that. Okay, so if you started putting in the coordinates of that point there, where we're going to put the can, which coordinate can we figure out now, and what would we have to do to figure it out?
Okay, well, 13 3/4 is from here up.
Okay.
So that's not what we want as a measurement from here down. As
Oh,
we're
that's
looking at
right.
the
We
y
want it from the
measurement.
x-axis. So we have a 29.5.
Okay.
29.5. Isn't this exciting? Math teachers using a calculator to do these simple subtractions. Minus 13.75. And we get, of course, and Melanie knew that a long time ago, 15.75.
Okay, so 15.75 is this distance, and that's from the origin down, so that's going to be a negative again when we actually use it.
Okay. So which coordinate of the point do we have available now?
We have our y coordinate here.
Okay.
Now, let's see, we used to know an x coordinate here, but I don't think I know an x coordinate here.
Remember that problem we did in math class where we would say, we have to locate a point. We'll give you the x coordinate, you find the y, or we'll give you the y coordinate, you find the x. Remember those kind? You wondered why we did those. Well, right here, we have a y coordinate, and we need to find
the x coordinate.
But we can't measure it, but we can get it from our equation.
Since now we have a y coordinate, and we have an a value, what we don't have is an x coordinate, but we again have just one variable missing, so I assume we can do that.
Okay, what number do we have to put in place of y to do that?
This number, and again, I have to keep reminding myself that I'm going down because this is the negative value, so we're going to put in negative 15.75.
Okay.
Negative 15.75 for the y value equals negative 0.0148 times x squared. So to solve for x, this number is attached to it, and before we get rid of the exponent here, we're of course going to get rid of anything multiplied. So we're going to divide this negative by this negative, and when we divide the two negatives, we'll get a positive. So what will we get there? That one I don't know off the top of my head.
No, that's a little messy, isn't it? 15.75 divided by 0.0148. And my calculator says 1,064.189.
1,064? Point
189.
189. So that's what x squared equals.
Right. So what do we do to get x then? That's kind of far. That'd be way off to the end of the room, wouldn't it? That's something. We need a square root.
To undo that, we're going to have to take
Okay, so we're going to take a square root of that.
There's another reason why I'm glad that that's positive. Otherwise, it would be imaginary, right?
Yeah, this whole experiment might be an imagination. Yeah, I know. I get 32.6. Very close. 32.6 is probably as good as we're going to measure it anyway.
I think so.
32.6. Now, what do we do with that number?
Okay.
How does that show up on our graph here?
That's the distance from here to here, 32.6. That must be a distance along here. But of course, since we have the plumb bob, I think we can measure it on the white paper.
Oh, and then let the plumb bob hang there. Okay, that makes sense. We will get this position.
Let's see, if it was 32.625, that would be 5/8. So I think if anywhere close to 5/8, 32 and 5/8 would be good.
Okay. I think I've got it measured, positioned fairly well here. And there we go. And you said 32.
And almost to 5/8.
Okay, it's going to be right there. That's where it intersected that line I drew earlier. We'll get this out of the way. And will this work? Will mathematics find the position? That is the mystery here. Well,
can I cross my fingers?
Melanie and I, we don't have to cross our fingers because we believe in the power of mathematics. Now, do you believe in the power of mathematics? Is this going to be positioned?
Still?
Yeah, it's a little hard to tell, but it looks pretty good. Well, are we ready to test our mathematics?
We went across 32.6. It should be down 15.75. I hope it catches it.
Mathematics says that's where the can has to be to catch the ball.
All right.
And here is checking it out.
Ah! And it worked.
And
nothing
folks,
better than that.
With that, isn't mathematics wonderful? Do you see how mathematics and attention to detail takes the guesswork out of life? So hang in there, do your math, and it will serve you well.
Absolutely.
Thanks for tuning in.
Thank you.